Hi there, let's talk about some properties of continuous functions. This is section 5.3 for those students who are in my class. So first of all, let's set up a definition similar to what we did with the sequences in the last chapter. We'll talk about a function being bounded. And we'll say that a function, f, from some domain D to R, is bounded if, and let's get a good definition here, let's say that will be bounded if there is an m in the real numbers such that f of x is always less than or equal to m. And if I put an absolute value around this, then that means not only can it not get too big, but it means that it also can't get too close to negative infinity. So the absolute value would mean that we would be bounded both above and below. And of course this would have to hold for all x in the domain. So in a picture this would look kind of like so. We'd have a function like this, and we'd have some kind of domain down here. Let's say that this is D, and we just have to make sure that things don't flip out. So it kind of goes from somewhere and maybe goes up and down, doesn't really matter, but it has a high value that it gets up to and it has a low value that it gets to, but it doesn't go off towards infinity in either direction. Okay, so just to make sure we're understanding this, what would be some examples of functions that are continuous on 0, 1 but are not bounded, that sort of flip out on us? Well, let's consider a first basic function, like maybe a reciprocal function of 1 over x. Notice that on the interval from 0 to 1, just on the open interval from 0 to 1, the 1 over x graph looks like, let's see, it gets 1 would give me 1, so there's a value of 1 at 1, and on this end it would fly off towards infinity, of course, right? Because as you get closer and closer to 0 on the x-axis, the reciprocal gets very, very close to infinity. So this function's continuous on the open interval 0 to 1, but it is not bounded. It flies off to infinity. There are possibilities that don't just fly off to infinity. There's some that may fly off to, for example, negative or to negative infinity. So consider a function like negative 1 over x squared. So again, just on the interval from 0 to 1, sticking in 1 would cause a negative 1. So this graph would be right here, and this time because of the negative, it would go off negative 1 over x squared would flip off towards negative infinity. So this graph right here would also not be bounded. This one would be, the first graph would be bounded below, of course, but not above. And this one would be bounded above, but not below. And finally, just as a more fancy example, consider the function tangent of pi over 2 times x. So this would be a period changer, right? This would be, I guess, a vertical compression factor. And on this particular graph, we would have only going out to 1. I purposely compressed it by pi over 2, so that way we would see that the graph would fly off. It'd have an asymptote at 1, and so it would fly off towards infinity in the other direction. It would go this way. 0 would be 0, of course. Tangent of 0 is 0, so tangent of pi over 2 times 0 is also that, is also 0. And notice that this function is also bounded below but not above, so it's very similar to 1 over x, but in a different kind of way with a dramatic trig function. Okay, so let's go with our big theorem this unit. Our big theorem will be if D is a compact subset of R, and we're going to suppose that f is a continuous function going from that domain into R, then it turns out that fD is compact. It's going to be compact. So recall, since we're working in R, maybe we should remind ourselves of Heine-Borel, the Heine-Borel theorem, because in R, the Heine-Borel theorem was the theorem that said that if you are in R, a set is compact if and only if it is closed and bounded. And I warned you that when we learned Heine-Borel that this would be the stuff that makes the calculus work. It's the stuff that makes dreams come true. That we have a compact set if and only if it's closed and bounded. And that's why a lot of our theorems in calculus rely on closed bounded sets, because those are compact. And compactness turns out to have the properties that we like. The definition of compact, strictly speaking, was that every open cover of the set yielded a finite subcover. So that will be the proof technique that we'll use here, is we're going to take an open cover of f of d, because we're trying to show f of d is compact, and hopefully from that we'll be able to parse through and pick up a finite subcover that would also still cover up f of d, but do it with only finitely many sets. So let's see if we can do it, eh? Let's let f equal the set of O alpha arbitrary sets be an open cover of f of d. And let that be an open cover of f of d. Remember, that was the set of the image. That was the image of that domain. And we want to try to show that it is compact, so we're letting f be an arbitrary open cover of f of d. We need to show that f has a finite subcover. So, using what we have so far, we know that since f was given to us to be continuous, since f is continuous on D, we know from the previous lecture, 5.2, that we know for each OA that is in this family of sets, we know there is a preimage, or let's call it an O prime of A, such that if we take O prime of A and intersect it with D, that this would be equal to the inverse image of the OA. We have to make sure to intersect it with D, because potentially there could be some other elements that were not even relevant. So the OA prime might have some extra things that were not part of the domain, but when we intersect it down to the domain, we end up getting just things that were inside of the preimage of the OA. But what would that give us? So thus, we would end up getting that D would be a subset of the union of all of the inverse images. So f inverse of G alphas, f inverse of O alphas, O alpha primes. No, not O alpha primes, just O alphas, because those are the ones in the other set. O alpha. But then this would be a subset of the union of the O prime alphas. Alright? And remember, the union here, I don't need the intersect D's, because if there were some other things that weren't in D, this would still be covering it. D would still be a subset of this object. Okay, but notice that since we have here that this is the union of all the inverse images of all the OAs, what we're getting here is a cover of D. Right? We're getting that D is a subset of this infinite set. But remember, from the assumption that D itself was compact, right? D is a compact subset. So that means that since we have this open cover, let's go into the next part of the argument. Since O prime alphas, since these preimage sets are an open cover of the compact set D, we know there is a finite collection of them that also covers D. There's a finite collection with D being a subset of only the O prime A1 union, and a finite subcollection here up to the O prime AN. It's only finitely many. then if we just make sure to intersect these down to D to make it relevant, we're not going to affect D over here on the left at all. We'll just make sure that we take each one of these O prime alpha 1s and intersect each one with D. Union, and finally at the end we'd have an O prime alpha n intersect D. But then what would these imply? Well, because of the way that we picked the O prime alphas, the way that we picked the prime ones, we now get what? We get that f of D would be a subset of the images, not the pre-images, but the images after we send these maps or send these sets under the F map. So we get that O A1 unioned all the way up to O A n. So f of D is a subset of this finite number of the original O's. So this is a finite cover. This is a finite cover of FD, so FD is compact, just as needed. So yay! We have the big theorem for this unit, that when we have a compact set and then we use a continuous map, it is sent to a compact set. So via Heine-Borel, that means that, remember, a compact set if and only it's closed and bounded. So if we have closed and bounded sets, they get sent to closed and bounded sets. Okay, now the first theorem that you may recall from a class like calculus is a Minimax Theorem. I call it Minimax. I don't know if that's the professional name. But it says that if D is a compact set of R and we have F a continuous function from D to R, then F will actually attain a maximum and a minimum value. It'll actually hit the maximum and minimum. So let's see how we might go about proving this. Well, we have that D is a compact subset of R and F is a continuous function. So the big theorem that we just did tells us that F of D is compact. F of D is compact. So for compact, that means that if F of D is compact, there is a minimum and there is a maximum. So F of D, right, it's bounded and it's closed, so it contains all of its limit points from the topology. So F of D has some kind of minimum. So it has a min, say at some value like y1, and it has a maximum, right? Bounded, closed. So it has a maximum, and let's call this one y2. Say at y2. Okay, but these are both in F of D, right? Since y1 and y2 are in F of D, there are x1 and x2 located in D with f of x1 equals y1 and f of x2 equals y2. Right? F of x1 equals y1 and f of x equals y2. Thus, f of x1 will be less than or equal to f of x, which will be less than or equal to f of x2 for all x in D. Right? This is true for all x in D. So we're getting what we want here. Right? So we can find these points. So we got a point that's higher than everything else, that would be a maximum, and a point that's lower than everything else, and that would be a minimum. MWO. Maybe we should draw a quick sketch of this so that we can see what it looks like. So remember, we've got a closed and bounded set, so for the sake of simplicity I'll just assume it's essentially an interval here, like A going to B, but technically any closed or bounded set would work. And all it's saying, all this theorem is saying, is that no matter what the function does, right? Maybe it goes up like this and over like that, but it's closed and bounded, so we have to make sure that we have endpoints on it. And it's saying that this function here will always attain some kind of value that we can call the maximum. So in this picture it looks like the maximum would be right there. And it will attain a minimum, which in the picture looks like it's actually on the left endpoint here. So we're just saying every closed and bounded subset, compact subset of R, will attain a minimum and a maximum. Okay, now it's really important in the Minimax theorem. This is vital. It is important that D be compact. Consider an open interval like 0 to 1. This is not compact in R, right? This is bounded, right? An upper bound would be 1 and a lower bound would be 0. It is bounded, but it ain't closed, right? This is not a closed subset. So what would be an example of a continuous function on 0, 1 that does not actually attain a minimum or a maximum? Well, let's just take a relatively simple example. Let f of x equal just the standard parabola. Let f of x equal x squared. On the open interval from 0 to 1, remember open interval, 0 to 1, on the left we would hit close to 0, but it's open, so we never actually quite hit 0. And then on the right we would hit 1 or get really, really close to 1. And remember, y equals x squared, or a parabola looks like that, but we never actually hit the maximum. Right? We get 0.99, 0.999, 0.9999999, actually technically squared, but we get really, really, really close to 1, but we never hit it. We never actually hit the maximum. And similarly, on the left, we get really, really, really close to 0, but we never quite hit it. We're never going to hit our min. Okay, now we're going to need to do a lemma here for our intermediate value theorem. Our intermediate value theorem will come up next, but we need to have a lemma first so that we can make sure to prove our intermediate value theorem. And our proof, or our lemma, will be that f is a function that goes from a, b to r. So we're going to move ourselves over to actual closed intervals because we know those are compact. We're going to let this be a continuous function, and suppose that f of a is less than 0 is less than f of b. So there's some, on one endpoint you get a lower and one endpoint you get higher than 0. So we've got something in between 0. So then we're going to say that there has to be a point in the interval from a to b such that f of c is actually literally equal to 0. We're going to hit 0 dead on. Okay, let's start to prove this then. Let S equal the set of x in the interval from a to b such that f of x is less than or equal to 0. Right? F of a is definitely less than 0. Right? So this is going to be the set of all points that are either less than or equal to 0. So this is not empty, right? Since f of a is less than 0, notice a is certainly in S, so we got something in there. And furthermore, additionally, since b is the right endpoint, that means none of the values will ever be bigger than b. None of the x values will ever be bigger than b. So additionally, we see that S is bounded above by b. Right? So we have a non-empty set of real numbers that is bounded above, so we have a soup. That's the completeness axiom. So we will let C be the soup of S. That looks like I'm saying CB, right? So we will let C be the soup of S. Okay, here's going to be our big goal then. I'm going to take that thing and I'm going to want to show, I'm not assuming what I want to prove here, but I want to show you, I want to convince you that f of c is that value. F of c is the one that is going to be equal to 0. Let's just draw a quick sketch of what we have going on here. Looks like we have an f of a, here's a, and we're below the x-axis. And then over here we have a b, and we're above the x-axis. So we don't know what our graph does, but it comes like this maybe. And what we found now is that we found this value right here that we're going to be calling c, and that's going to be the furthest x value that gives me less than or equal to 0 potentially. We want to show that f of c equals 0. let's see if we could do it. So I'm going to do one direction of the argument, and you can do the other one on your own. You can follow along in the book if you'd like to see the upper bound argument, but we will do the lower bound. We'll do the lower bound. I don't know which one the textbook does, but they're both similar arguments. We will suppose that f of c is not strictly equal to 0. We're going to assume that it's, we're going to assume that f of c is not actually equal to 0, that it's actually somewhat strictly less than 0. Okay, what would that mean if that were true? Well, then there would be a neighborhood. There would be a neighborhood u of c with f of x less than 0 for all x that happen to be in that neighborhood intersected with AB. And let's go back to the picture and check this out. So what I'm saying here is that we're going to assume that we're not hitting that cute little c value. We're saying that c is actually strictly less than 0. So c might be right there. And I'm saying that if we have a value that's actually less than 0, f of c is less than 0, then we can find a little window around here, and that'll be my u, where f of c is always less on that particular interval. But this is an entire interval, right? This is an entire interval, so I'm going to go pick out a value inside of that interval. We're going to let there be a little p-value and see if we can find that p-value that's inside of this interval and see if that causes any problems. Hopefully it'll cause a contradiction. Okay, let's see if we can find that thing or see what's going on with it. So now, since f of c was less than 0 and f of b was bigger than 0, we can see that c is definitely not equal to b. Right? Functions have unique outputs, so if one of them's negative, one of them's positive, then they cannot be the same input going into the function. And that's important so that we were not getting too far to the right hand side. We actually get somewhere in the middle. So we see that c is not equal to b, and so there must be, u must have a point, call it P, just like I did in that previous picture, and for this point we're going to have that C is less than P is less than B. Right? We find a little point that's inside of that interval that we're still over here, so we're less than C and in P. Oh, sorry, P is less than B, right? It's further than the right endpoint, but it's also bigger than that value C. But that's a problem, isn't it? Because since it's in U, remember U is the set of all these points such that the whole neighborhood is less than 0, so we're getting that f of p happens to be less than 0, and, probably not a but here, but an and, p is bigger than c, contradicting that c was the soup of S. Right? It was supposed to be bigger than all of the points in S, but we just found another point, P, that was actually bigger than C, and it is also in the negative range. It's also in the negative part of the graph. Right? So that's how our pictures, so that's why our picture over here is a violation, because we're finding this point P that actually hits below, but C was supposed to be a soup. C was supposed to be a soup of S. So that, of course, is a contradiction, and therefore it is not possible that f of c is less than 0. So you should try to do a similar type argument, verify at home, that f of c must be bigger than 0, or f of c bigger than 0 is also a problem. I did the less than, you tried the bigger than, very, very similar argument. Okay, and with that argument, or with that, now we can prove the big intermediate value theorem, big famous theorem from calculus. If we have f as a function going from this compact set AB into R, and we know that it's continuous, then if k is any value that's in between f of a and f of b, then there has to be a c in the open interval from a to b with f of c equaling k. So in a picture, just to remind you, again, this probably doesn't need any introduction here because it's so famous, but if we have an a here and an f of a value, say right here, and then the function kind of goes maybe up, and let's do a different color so we can see this easier. So it goes kind of up, and then maybe it comes down a little bit, and then it comes up to here, who knows. But then over here we have a b value, and over here we have an f of b value. Then what the theorem is saying is that if you give me any old k that's in between f of a and f of b, then as I come over here, I can find points in the open interval from a to b such that when I take the functional value of them, I hit k. So this right here would be a potential c. Notice that there doesn't have to be a unique one. This right here would also be a happy point that gives me c, and this one over here would give me a happy point that would be a potential c value. So there may be more than one, but we know that there's at least one. That's what intermediate value theorem dictates. Okay, now watch this proof. This proof is gorgeous, and it's really, really powerful for all of the applications on the intermediate value theorem. So with loss of generality actually, but I'm going to do an argument for f of a being bigger than f of b. You try f of a being less than f of b on your own. And I remember our textbook does do the less than argument. So after I perform the bigger than argument, you should pause the video, try the less than argument on your own, and then check the textbook to verify you did it correctly. So here's our proof for bigger than. We will suppose that f of a is bigger than f of b. We're supposing f of a is bigger than f of b, and let k be any number, be between f of a and f of b. Since f is continuous and k is constant, the function g of x, defined to be k minus f of x, is continuous. Because the sum or difference of continuous functions is continuous. So this g of x function defined is continuous because k is constant and f of x was assumed to be continuous. Okay, now what do we notice? Well, what is g of a? G of a would be k minus f of a. But remember, we assumed that f of a was bigger than f of b and that k is between them. So if we take k and we subtract from it f of a, we're subtracting a larger number, so this must be less than 0. And what else? Well, g of b would be k minus f of b, and since k is bigger than f of b, if we take k and we subtract this smaller number, that will be bigger than 0. Right? Thus, the lemma that we just showed, the lemma gives us what? The lemma ensures there is a c, I guess in that I don't need that article, there is a c in the interval from a to b with g of c, which notices k minus f of c, will force this to be equal to 0, and so k would be equal to f of c. Because if k minus f of c equals 0, then k would be f of c. So that's a half of an MWO. because we still need to do the case where f of b is less than f of a, or where f of a is less than f of b. So verify at home, try on your own, verify at home the f of a less than f of b case, and check it against the textbook, because that's literally the case that is done in the textbook. Okay, now for all you applied ladies, you wanted to see some applications finally, right? So here's some applications. First claim, every positive number has a positive nth root. Prove that every positive number has a positive nth root. Every positive number, so let k be a positive number. Let k be bigger than 0. Let n be a natural number, because we're going to take the nth root, and define f of x to be equal to x to the power of n. In the last reading, we saw that all polynomials are always continuous. So this x to the n function is a continuous function. Okay, notice, remember I said the same argument will apply often when we're using IVT. Notice that f of 0 is equal to 0 to the power of n, which is 0. And since k is bigger than 0, this is certainly going to be less than k. Also, if we let b equal k plus 1, then we can see what happens if we take b to the power of n. Well, since b is equal to k plus 1, this would be 1 plus k to the power of n. 1 plus k to the power of n is bigger than 1 plus kn by Bernoulli's inequality. And since n is an integer, or n is a natural number, sorry, and 1 is a positive number, this is certainly going to be bigger than k. So we have that f of b is bigger than k. So f of b, right, the thing that you get when you stick in b, is bigger than k. Right, so we have f of b is bigger than k. We have 0 is less than k. So by the intermediate value theorem, so IVT implies what? There is a c in the interval from 0 to b such that with f of c is equal to k. In other words, that means that c to the power of n would be equal to k. And that c is an nth root of k. This c is an nth root of k. Nice. And notice it's positive because it is on the interval from 0 to b. Right? So this is f of 0 less than k, and f of b is bigger than k. Right? So I guess I should put an f in front of this so it's clear. This is f of 0 is less than k is really what we cared about. F of 0 less than k, f of b bigger than k. So k is between f of 0 and f of b, so there's a c between 0 and b that forces this to be the case. So every positive number has a positive nth root for any natural number n. Way. Okay, let's try to see how this could apply to an equation. Let's take a tough equation like cosine of x equals x. We're going to show that there's a solution to this if we assume that cosine of x is continuous. By the way, cosine of x is continuous, but we didn't technically show that, so we're just going to have to accept that on faith, or you can try to verify on your own that that's true. But if cosine of x is continuous, then there is a solution to x equals cosine of x. For those who had me for Math 2x, you might recognize this technique as what I did with my graphing on the calculator to find roots of complicated functions or complicated equations. So let f of x equal x minus cosine of x. This function is continuous because x is continuous, and we're assuming that cosine of x is continuous. Notice, what is f of 0? 0 minus cosine of 0. Cosine of 0 is 1, so this is equal to negative 1. And what is f of some number? We just got to get positive, remember, because we just want to find a zero or solution to this. So I'm going to take pi over 2 because that's equal to pi over 2 minus cosine of pi over 2. And cosine of pi over 2 is 0, so this is pi over 2, which is positive. So f of 0 is a negative number. F of pi over 2 is a positive number. So IVT implies there is a c in the interval from 0 to pi over 2 with f of c equal to any number I want between -1 and pi over 2. So in particular, we're going to let that f of c, remember f of c is c minus cosine of c, and we're going to say that that's equal to 0, because 0 is a number between -1 and pi over 2. So add cosine of c to both sides. C would be cosine of c. I didn't even figure out what the solution was, but I know that a solution exists. IVT is a great theorem. Okay, last theorem for this one, last theorem for this lecture. Let's let I be a compact interval and suppose f is a continuous function from that interval to r. By previous theorem, we know that f of I is certainly going to be compact. So f of I is a compact, but what makes this one different is I'm not just going to show that it's compact, but if I is an actual interval, then this will actually end up being a compact interval. So in general, a compact set is closed and bounded, but we're going to have it as an interval here. So if we do have an interval as the domain, the range will also be an interval of numbers. Okay, I'm going to do a double set containment argument here to show we're actually going to find out what that interval is. We're actually going to locate what it is and prove that it is a double containment. F of I is equal to this closed interval. Remember, it's closed. That's enough because it's a closed set, a closed bounded set that is compact, and it will show that it's an interval. So forward direction. By the Minimax theorem, we have a compact set as the domain, so we know that we're going to attain a minimum and a maximum. So by Minimax theorem, there are values x1 and x2 such that f of x1 can be made less than or equal to f of x, which could be made less than or equal to f of x2 for all x in the interval. Okay, so if we find these, if f of x1 is going to be the small one, let's just call little m equal to f of x1. And if f of x2 is going to be the big one, we'll let capital M equal f of x2. Notice this is true for all x's in I, so it's actually pretty trivial now. This is just true that f of I, f of every single value that's in x is between f of x1 and f of x2, so f of I is definitely a subset of the closed interval that goes from m to capital M. So that's this containment. We have a one direction containment. Let's go for the backwards containment now. So we need to show that if over here we showed that f of I is a subset of m to m, little m to big M, we're going to have to show that little m to big M is a subset of f of I. So let's try that. Well, if m equals m, if the minimum was equal to the maximum, then we would just have a single point, right? Then f of I, if the minimum is equal to the maximum, then all of the points are just the single point. So then f of I would be a single point, and that's kind of a trivial interval, right? That would be an interval that starts at m and ends at m, because that just is the singleton m. So in that case, it's kind of done already. That's definitely a compact. It's a really small interval. It's only 1 point. let's go with, instead of that, let's suppose instead that m is not equal to m, but m is the minimum, capital M is the maximum, so we're going to suppose that little m is actually bigger than capital M. Let k be any element in between little m and big M. So k is an element between little m and big M. Well, since f is continuous, we have the IVT. We have the IVT, the intermediate value theorem. So there is a C located in the interval that extends from m to capital M, little m to capital M. I guess this would have to be an open interval by that theorem, so little m to big M, with f of c equals to k. Thus, the open interval m to m is certainly going to be a subset of f of I. I'm now realizing that my choice of little m and big M is not very nice for showing which one's larger and which one's smaller. So let me make this a little bit more extreme. This is the interval m to m, and this is m to m. The one on the left is always the small one, and the one on the right is always the big one. But we didn't actually get the endpoints technically, but remember that we really did, because m and m were x1 and x2 from I. x1 and x2 were taken from I, and they actually hit the minimum and the maximum, because the Minimax theorem says that you actually attain those minimums and maximums. Also, so thus we get all the open interval from n to m, little m to big M by the IVT, and we also have m and m are in f of I by Minimax. So therefore, m to m, let's make this more extreme again, therefore m to m is a subset of f of I. And so we have the containment going the backwards direction now. We have containment going f of I into m to m, and over here we have m to m being a subset of f of I. M, W, L, O. Definitely compact because it's a closed bounded subset of real numbers. So Heine-Borel tells us this is compact, and it is an interval because we showed it's actually equal from little m to big M. So your homework for this section is going to be problems 1 and 2, 5 and 8, which are applications, and then 9 and 13. Okay, best of luck.